Hello and welcome to my garage. Last time I was with you, we were discussing density and we were testing out the effect of salt in water on the flotation of a ship. And if you remember, what we had was we had a ship in freshwater and we had a ship in an equivalent of the Dead Sea, and we were having a look at the difference that made. If you've not seen that video, then have a look at it. And the previous one, which dealt with buoyancy of ships. Now today we're moving on to something which is just as important as buoyancy, because I'm sure you would agree that if you're on board a ship, it's very, very important to you that it floats. But I also feel that it is extremely important that it floats the right way up. And when people ask me what is it that naval architects do, if I'm feeling a bit flippant, I say we make sure that ships float and that they float the right way up. And so the stability of a ship is a really important part of our job. And there's a whole theory behind stability which I'll cover in another video. But for today, what I'm going to be covering is how we test the stability of a ship in order to start the process of working out whether it's adequate for it to be safe at sea. So what we're going to do is we're going to do an inclining experiment. So what I've got here is I've got this ship, which you'll recognise from the other videos if you've seen them. And it's rigged up with a little bit of gear. And I'll give you a closer look at this shortly. But what's on board the ship just now is a pendulum. And the purpose of this pendulum is to swing as the ship heels over and allow us to measure how far over the ship has heeled. And I know that from where the camera is just now, you can't get a very close view of this, but I will give you a view. And as well as that pendulum, we have this structure here. You'll see what that's for shortly. And we also have 4 little weights. Now on a full-size ship, these weights would be obviously very much bigger. You need weights which are in proportion to the weight of your ship. So on a ship which was perhaps a fishing boat, maybe a 60-foot, 80-foot fishing boat, something like that, what's very often used are 50-gallon water barrels filled with fresh water. They're a good size, they're a good weight, they're big enough to cause the boat to heel over a measurable amount, and that's what we need to do in order to test its stability. On a larger ship, a seagoing oil tanker, bulk carrier, something like that, you would be looking at something like very large concrete weights, and they'd have to be lifted by a crane. The 50-gallon water barrels can be shifted by people. You just need a couple of men to shift them, or muscly ladies. And that works fine. And then what you would put on board your boat as well as your 4 weights is you would put 2 pendulums. I've not put 2 pendulums on this boat simply because it would take up too much space on board. But 2 pendulums gives you a huge advantage in that if you have an error in your reading on one pendulum, you can see the correct reading from the other pendulum. It allows you to cancel out errors. And create a result which is an awful lot more accurate. That's the same reason why you have 4 weights rather than just having 1. So, there are a few measurements that we need to take before we get started with the actual experiment. And one of these measurements is the weight of these inclining weights, as we call them. So we need the weight of each one. And so I've got my scale here. Measure them each in turn, making sure that the scale is zeroed in between each one, and they're all around about 24 grams. If the differences between them were significant, we need to take account of that, but in this case these 4 weights are very, very similar, and so they're all coming out at more or less the same weight. Now another weight that we need for this to work is the weight of the ship itself, because what we're going to do is we're going to move the weights to and fro on board the ship, and then we're going to measure how far it heels over. And how far it heels over depends on how heavy it is, and also depends on how stable it is. The more stable it is, the less movement you'll see. The less stable it is, the more dramatically it will heel. In real life, you cannot put a ship on the scale, as I said in my first video. They're simply too big. And so what you would do, I'll show you later how you would do this on a full-size ship. But for this small ship, we can just weigh it on the scale. I'm going to put these weights on board because we have to weigh the ship as it's going to be in the experiment, and that means with all this gear and the weights on board. So let's see what sort of weight we're getting. 1.08 kilograms for all that lot together. Okay, and I'm going to give you a closer view of the gear on board the ship, and we'll carry on with the experiment. There you can see the pendulum there, and as the vessel heels, the pendulum leans over. There's a ruler there which is going to allow us to measure the deflection of the pendulum, in other words how much it's moved from side to side in millimetres. And another piece of information that we need is we need the length of that pendulum from the pivot point at the top to the measurement point at the bottom. So I've got a ruler here, and we're measuring the height of that pendulum at about 10.5 centimetres, so that is 105 millimetres. Okay, and now this is where you find out what this structure in the bow is and where you get a really close view of what is going on. Okay, and now we're ready for our experiment. Okay, so in order to do this experiment, we've got to make sure that our pendulum is zeroed when our boat is floating upright. At the moment, the pendulum is tending to lean slightly to port. No ship in the world was ever made perfectly symmetrical, and so inevitably the pendulum will be slightly off zero. In real life, if you were doing an inclining experiment, actually you wouldn't have a pendulum with a pre-marked 0 point. You would use a strip of paper, and you would mark the 0 point before you started the experiment at whatever the upright position was. In this case, as I say, this pendulum is tending to lean over, so we'll just adjust it slightly to try and get a fairly reliable 0 point. That's still a little bit over. Come on, you can do better than that. There we are, that's not bad. All right. Now, on the a real inclining experiment on a ship which is too large to fit on a scale, the way that you would assess the weight of the ship before you started would be by reading the draft marks. So we'll read the draft marks on this vessel, even though we're not going to use that data. We're going to use the data that we took from the scale. But in real life, this is what you would do. You would read these draft marks, and then you would go to your ship's drawings, which show you the shape of the hull, and you would use that draft mark to calculate the volume of the underwater part in order to work out the volume displacement, then the mass displacement, then that tells you how heavy your ship is. So our draft on the port side is measuring at just about bang on 2 centimetres. You note that that is a little bit more than the draft that we had in the first video. That's because of all this extra weight that is on board. On the port side, so that was a draft on the starboard side. Don't know if I said starboard or port. On the port side, we're looking at a little bit of a list. So it's about 2.5 centimetres on the port side, 2 centimetres on the starboard side. So you'd have to take account of that list in your calculations. Okay, and then we start the experiment. I took that draft wrong because the draft should be taken with the weights in their correct positions for the experiment. So we start off with 2 of the weights over on the port side and 2 of the weights on the starboard side. We're going to put 2 of them on the upper deck because we don't really have anywhere else to put them. And we're going to, through the experiment, one by one, move the weights across to the the opposite side and see what effect that has on the heel of the ship. So the last piece of measurement we need before we can actually just do this experiment is we need the shift distance. In other words, how far are these weights going to move from side to side? And I've got them arranged as far as I can so that they're all moving the same distance. So I'm going to say if this one moves from here to there, how big a distance is that movement? And let's get our ruler and measure that. So from the outer side, I'll say from centre to centre is really the most correct way to measure it. So I'll measure from centre to centre. We're moving it by 70 millimetres. All right. Okay, so let's go back to our 0 position. Check that our pendulum is more or less at 0, and it's not quite. It's not inclined to correct itself. That's a little bit too far the other way. Great thing about using Lego is it does allow a little bit of correction. So if you're looking through the camera, you should be seeing the 0 point is marked with number 4 because it's an 8 centimetre ruler. But that is what we're treating as a 0 point. If the 0 point is not perfectly in the middle, it's not actually the end of the world, because as you'll see as we go through the calculation later, the corrections that we make will account for a slightly off-centre 0 point. So where are we at? I feel it's now gone a little too far to the other side. Are you sitting? Are you centred now? I think that's as good as we're going to get it. Alright, so inclining experiments are tricky for a number of reasons, and one of those reasons is that in order for the test of stability to work, the ship has to be freely floating. And it's very difficult to have a ship freely floating and keep it under control. If you look at this ship here, even in this perfectly still water in this little tank, I'm holding it by the bow rope and its stern is floating off to one side. And of course that happens on a full-size ship as well. In order to have an inclining experiment, you can't have the ship tightly tied to the quayside or the ropes might interfere with the experiment. You have to have them as loose as possible. And so what happens is that the ship will float in and out. It will float in, hit the quayside, it will float out, strain its ropes. It will float in and hit the quayside, and it does that throughout the experiment, and every time it pulls on its ropes or bumps on the quayside, it disrupts the results of the experiment. So it can actually, although this looks like a simple experiment, and it is, and it won't take very long here, it can take hours to do on a real vessel because of the difficulty of keeping it floating neatly. Now, other important things about an inclining experiment, which we're not having to worry about here because this is a simple toy boat, is that any weight which is not normally part of the vessel ought to be taken off before the experiment, and anybody on board who is not necessary for the experiment needs to come off as well, because any extra weights can change your result significantly. And in particular, if you have any liquid moving around on board, like a half-full tank, that will make the stability look worse than it really is, because as the vessel heels over, the liquid will flow to the downhill side, and that will cause the stability to look worse. It will cause it to heel further than it otherwise would. It's not possible to get an ideal setup for an inclining experiment. There's always a few extra weights on board, or something's missing that ought to be there. There's always a little bit of liquid moving, but we try to get it set up as near ideal as we possibly can. Okay, so we're going to start moving these weights, and the first thing I'm going to do is I'm going to move the foremost weight. And I will, because as I'm doing this, I can't clearly see the pendulum. I'm not going to read off the results as I do it. I'm going to read them off the video later, and then I'll show you how the calculation works. So first of all, we move this weight over to the opposite side, and we allow the vessel to settle. Now, I'm a little bit concerned that that pendulum's not moving freely there. No, actually it is. Okay, looks like we've got a settled reading there, and you'll be able to see what that reading is. I'm going to move the second weight, and this is the most extreme position. And this is the point where the the position of my smartphone starts to worry me a little. I wanted to use the old smartphone with the broken screen for this, but unfortunately its battery is so bad that it can't work without being plugged in. So the old smartphone with the broken screen is doing our overhead shot just now, and this is my actual phone. So we're hoping for no capsizes today. Alright, so having measured our extreme heel, we're now going to move this weight back to its original position. Allow the pendulum to settle. And then we're going to move this weight back, and that ought to bring us back near zero. Having done many inclining experiments in my life, I don't expect it to actually come back to perfectly zero. There are many sources of error in inclining experiments, so I expect there to be a slight error all the way along, and this, as I say, is why we use 4 weights and 2 pendulums, so that we get 16 readings at the end of the day in order to get rid of those random errors. Okay, and I'm going to take this weight now and move it across to the starboard side, let it settle, and this weight, move it across and went into our extreme position again. And once again, we hope for no capsizes for the sake of the smartphone. No capsize. Thankfully, we're lucky. Bring this one back over, let it settle, and then bring this last weight back over, and we should return to near zero. Now that was quite quick. In real life, this is not a quick process. You see that the boat is rolling pretty well all the time, very slightly, slight rocking motion. A full-size vessel does that as well, but the nature of a full-size vessel is that it rolls more slowly, and that its momentum is so great that it keeps rolling for a very long time. And that means that the pendulum doesn't settle nicely like this. The pendulum continues to swing for a very long time after the weights have moved. We put the pendulum into a trough of either water or oil to slow it down and damp it swinging. But even so, it still will continue swinging for a very long time after the movement has been made. And also that means that rolling and the swinging of the pendulum means it's actually really quite difficult to get an accurate pendulum reading because it never settles. You're having to mark a midpoint between the extremes of the swings. You can see now on the video at the moment that the pendulum is swinging slightly. If you scale that up, you can imagine that it swings a really extreme amount on a full-size ship. And also, the longer your pendulum, the more accurate your result will be. So you want your pendulum to be as long as you possibly can make it, and that means that the swinging will be that much more extreme. Okay, so we've done our inclining experiment now, and what we're going to do is take these results and we're going to process them to find out how stable this ship is. And there's one more thing we're going to have to do before we do our calculation, and that is we're going to have to weigh all the extra weights which are on board this ship. I noticed when I was doing the experiment there that the smartphone actually was considerably destabilizing the ship. So if we were to take these stability results and say that's how stable this ship is, it would be extremely unfair. So what we need to do is we're going to need to do a calculation to account for all these extra weights in order to be fair to this ship. So, first of all, I'm going to measure where each of these weights are in terms of their centre of gravity. So we're going to be measuring all the centres of gravity up from the baseline of the ship. So this ship has a flat bottom, that's really very easy to do. And what I'm going to do first of all is I'm going to measure, and we have to be approximate about this, we can't be really accurate. I'm going to measure the height of the phone 15 centimetres above the interior deck of the ship, 150 millimetres above the interior deck of the ship. And I reckon that the centre of gravity of a smartphone is about halfway up. So that would make its centre of gravity about 75 millimetres above the interior deck of the ship. The smartphone holder, I'm just estimating this, you get good at this with practice. I reckon that it is about 50, its centre of gravity is about 50 millimetres above that interior deck. The pendulum arrangement, Reckon that centre of gravity, again, we're looking at maybe, do you know, its weight's quite close to the bottom. I think probably about 40 millimetres above the interior deck for that. And all of these pieces of Lego which are lying on the interior deck, I'm going to say that their centre of gravity is only about 2 millimetres above that interior deck. So how high is the interior deck above the baseline? It is in the region, and I'm working between the ruler on the outside and my finger on the inside, it is in the region of 2.5 centimetres, 25 millimetres above the baseline. Alright, so, and the other thing is, where's the centre of gravity of these inclining weights? So, each one of them is about 28 millimetres tall. The centre of gravity is not in the middle because the paint is sitting down towards the bottom. So I'm going to estimate it and say that their centre of gravity is about 12 millimetres above their base. This kind of estimation, I would, if this was a real ship and safety was depending on this, I would be using much more accurate estimations of these centres of gravity. What I would be doing is I would be using a drawing on a CAD program in order to work out where the centres of gravity of all the additional objects were. The other thing I want to know is how high is the deck that these lower weights were sitting on? It's about 4 millimetres above that interior deck. And how high is this upper deck above the baseline? It is 80 millimetres above the baseline. Okay, so what I'm going to do is I'm going to weigh each of these items in order to figure out what weight needs to be subtracted from the value that we had earlier. So we've got our scale here. Make sure it's properly zeroed. The first thing I'm going to weigh is my smartphone, which has some things to say for itself. The smartphone is 155 grams. Pretty light there. Not as light as the old cracked one, which is filming us now. That's why its battery life is so terrible. It's hardly got a battery. Okay, the pendulum. 23 grams. Smartphone holder. 94 grams. And the Lego deck structure in here. With its fixings, 31 grams. Don't think there's anything I've missed. I think that's everything that is now that everything has now been taken account of in terms of the weights that have been put on board, and we're ready to do our calculation.